website. You can join the Computer Society through the computer.org website. And if you want to follow us, we are fully on social media now, and the links are shown in the slides on this page here. So again, without further ado, it's my great pleasure to welcome Professor Swarup Bunia from the University of Florida.
Thank you, Dennis. So as you all have noticed that Dennis have shared all the address on the information. So please, whoever can participate, try to contact directly to Dennis or myself. And I will quickly hand it over to Swarup to start his presentation.
Okay, hopefully you can see my slides and you can hear me well. Thanks, Dennis. Thanks, Jonas. This is a wonderful opportunity, great initiative. Really appreciate that. Before I start, happy Thanksgiving to everyone. It's a momentous occasion, so I think everybody's enjoying. Wish you all happy and pleasant Thanksgiving. The topic of today's talk is Internet of Things security. I think all of you know about Internet of Things or IoT. I'll touch upon some of the security issues in IoT, particularly the issues that relate to hardware, electronic hardware, because as you know, hardware is basically the root of a system, root of trust for a system. That means the software stack, the communication layer, and everything rely on the trustworthiness of the hardware. Now, what are the security issues? What are the trust issues in hardware? And how it can help us to build secure and assured IoT. That will be the focus of the talk. Before I go into that, let's briefly introduce the institute which I belong to. It's called O&B NAMS Institute for the Connected World. The institute is developed a couple of years ago with the goal to make IoT foundational technologies for solving global problems. When we talk about global problems, we refer to the problems in the area of health, in the area of environment, agriculture, transportation, and many more. I have the privilege to direct the institute, and I have an associate director, Dr. Mithai, who is helping me with these efforts. These are the people who are involved in different activities in the institute. There are about 50 members of that, including some new hires. I call them the IoT Army. Together, we are doing exciting things. I'll talk about some of them today. These are mostly my own work. If you're interested to learn about other aspects of IoT, particularly how IoT can enable exciting applications in the area of healthcare, in the area of environment, and in the area of agriculture or so, please feel free to contact me. I'll be happy to do a deeper dive on any of these technologies. Now, before we talk about IoT security, let's set the ground. What is IoT? If you think about Internet of Things or IoT, in the web, there are a lot of different definitions. If you talk to different people, you will probably hear different definitions of that term. It's understandably pretty broad term, but before we talk about IoT security and trustworthiness, let's try to define the term as I view it. If you think about IoT, these are embedded systems, which are the systems, computer systems designed and optimized for specific use cases with tight hardware software integration. For example, digital camera, for example, MP3 player, things like that. If you look at the traditional embedded systems, which are there for last 30 years or so, which are different from the general purpose computers, and add generous amount of connectivity, then you add a good amount of smartness, and smartness can come from different aspects of artificial intelligence, particularly machine learning. And the smartness are there to make autonomous decisions so that the IoT device can make decisions itself. So it's like a recipe. And then on top of that, you add significant amount of interoperability. What is that? Interoperability means that a device should be able to talk to another device. It should be able to talk to a human user for the device. So interoperability can come in different layers. It can come in software layer, it can come in hardware layer, it can come in sensor layer, or in the communication layer. But in each of these layers, we need to have interoperability to make a heterogeneous network of connected systems where each device can talk to another, and together they can talk to the cloud through the internet. So that's IoT. It's again, it's like a recipe, but it's a very simple recipe. It builds on traditional embedded systems, but I will argue that it's not just old wine in new bottle. It brings in significant set of challenges when you talk about security or trustworthiness or anything else. It has a new set of challenges which will require significant rethinking. I'll talk about that. But before I go into the security aspects, let's look into the IoT architecture. Again, there may be different variations of that. Here we are talking about most common, well accepted 4-layer IoT architecture. At the bottom of this layer, as you all know, we have what we call edge devices or endpoint devices. These are the devices which are actually doing sensing, computing, and data collection. They are the one which directly interact with the physical world. So these are the endpoint devices like this Nest thermostat you can see here, smart thermostat, smart autonomous vehicles, smart router, wearables, things like that. They are connected among themselves through network, local area network, or things like that. And then together they're connected to the internet. And then these are connected to the cloud. Finally, we have different set of applications which either run in the edge or in the cloud. So this 4-layer architecture is very important to understand what are the challenges and what are the opportunities for research innovations we have at each layer. So here, I'm just talking about some of the research innovations you can bring in each of the layers, which basically means that even though IoT emerges from embedded systems, there are significant opportunities for research contributions. And in the institute which I belong to, we are trying to address many of these interesting research challenges and bringing in new innovations at each of the layers of the IoT architecture. So let's talk about this emergence of IoT a little bit more. As you all know, we talked about the embedded systems. From the embedded systems, by including connectivity and smartness and interoperability, we are coming up with new breed of IoT devices which are enabling new applications. Now, this trend is giving rise to kind of an exponential growth in number of smart devices, smart connected devices, which we have today. If you think about the security for these smart and connected devices, one of the fundamental questions which, as a researcher, we need to address. Again, as a practitioner, also you need to address the same question: is that how can we protect diverse, which means they are heterogeneous set of devices, right? In your smart home, you might have a smart refrigerator connected to the smart light bulb, connected to the smart toaster, which is connected to your smart autonomous vehicle. So it's really a diverse set of connected devices which are talking to each other and building a heterogeneous network of system. So that's a diverse system, and it's highly complex because they're doing different things. And effectively, they will be used by naive users like my grandmother or like my 5-year-old daughter. They will be the one who would be, let's talking to the smart bulb or using a smart speaker like Alexa. They would be able to control some of the smart devices in the household, right? So the question is that when it comes to security, that means that with respect to different attacks, we have to protect this heterogeneous network of connected devices which are potentially being used by naive users, right? What makes it significantly more difficult in terms of security is that these devices are connected. The moment you have a connected set of devices, then the security vulnerability is significantly increased. Why? The reason is that if you have, let's say, a smart watch connected to a smart light bulb or connected to a smart thermostat, because there are diverse set of devices, the security vulnerability for the entire network is now dictated by the weakest link, which means that if your smart light bulb can be hacked effectively using that hacked device, one can talk to your smart wearable device and effectively can retrieve the sensitive private data from your smart wearable. So that's why connectivity is bringing new set of security challenges. If you think about IoT security, one question which you might ask is that what are new challenges in IoT security? What are unique aspects of IoT security? And that's a very fair question to ask. So in our research group, in collaboration with several of our faculties at University of Florida, we have been trying to understand what are the unique challenges of IoT security and how we can address them. So today, first I will talk about these unique challenges so that if you are a researcher, if you are a practitioner, at least you know that in the IoT regime, what are the new security challenges. That's number one. And number two is that I'll talk about some interesting paradigm of solutions. These are hardware centric solutions which can address these problems. So let's look at the first one. These devices connect with physical world. And that's obvious, right? If you think about smart thermostat, it's controlling the temperature of my house. It's really interacting with my house. Similarly, a smart toaster is interacting with me and my house. So these devices do interact with physical world, and many of them can have long, complex life cycle. If you think about the refrigerator, typically you run your refrigerator for 10 years or longer. If you think about an autonomous vehicle, you run it for maybe 10 to 15 years. If you think about industrial IoT or even military IoTs, the Internet of Things devices which are used in defense for our nation's security, many of these devices like military drones, military weapons, military helicopters, they may use a significant amount of autonomy, and you can call them IoT devices. These devices would have long, complex life cycle, and during that long, complex life cycle, which will involve different usage scenarios by different people, which will have different levels of access to the device, the security requirements would evolve over time. If you think about a span of 15 to 20 years, even for a 5 years, security is always a moving target. The requirements evolve, the standards evolve, and not only that, new attacks would surface because attackers become smarter, right? Now, you need to be mindful about this evolving security target. You need to be mindful about the evolving attack space, and your system has to be able to address those evolving requirements. That's a very, very important point. Another point to note here is that IoT devices are mass produced in the same configuration where millions of edge devices are produced with exact same hardware software configuration. What is the problem with that in terms of security? Of course, that's very advantageous in terms of repairability, in terms of the cost, right, and all those things, or even interoperability. But if you have the millions of devices with exactly same configuration, from an attacker's point of view, it's really great, because what the attacker has to do, he spent his or her time, significant amount of time and resources to understand the security issues in one device and potentially break into that device, figure out the vulnerability in the device to break into, and then use that knowledge to compromise another device of exact same configuration, right? So that's why IoT devices are extremely vulnerable. I'll talk about an example, a real life example that happened, and that requires us probably some kind of configurations which can be customized for specific instances. So we'll talk about some of the hardware-centric solutions there. And then the next one is that many of these devices are never intended to be connected to the internet or connected to another device. I can give you an example of the smart light bulb. Many of these devices are so tiny, they run at such a small power and cost budget that it's not possible to run even a stripped down version of operating system there, which means that the typical internet security protocols, even high-end cryptographic protocols, are extremely difficult to run on those systems. Smart light bulb can be another one example, but there are many other examples like tiny sensors which are used for environmental monitoring or agricultural monitoring. They do not have provision to run complex security protocols. So that's why these devices can be extremely vulnerable, and because they are talking to another device, compromising one of them can compromise the entire system of connected devices. Then these devices talk to each other, which means that the communications often are machine to machine without having any human in the loop. If that happens, then you can easily assume that the authentication mechanism, because there is no human in the loop, can be weak in some cases. If you have something like that, then a machine can be easily leading to an attack itself. A machine can fake itself to be a valid machine because there is poor authentication, and there will be ample opportunities for man in the middle attack. So that's why this is creating a new paradigm of security vulnerabilities, which was there, but it's becoming more prominent in the IoT regime. Physical attacks are becoming a huge problem. I'll give you an example in a few moments. But the idea here is that the attacker can capture a device physically and then can do multiple things on that device. For example, the attacker can do something called mod chip attack, where the physical device can be configured to bypass the built-in digital rights management protection. I'll give you an example for that. Or they can do different kinds of side channel attacks to leak secret. Finally, if you think about IoT, I talked about this 4-layer architecture, right? IoT is not just one device. IoT is not just one layer. It's 4 different layers of heterogeneous set of devices with different hardware software integration and with a lot of connectivity in between. So just making one device or one layer secure is not enough. You have to make sure this entire set of connected devices and all the layers are secure to make the entire system secure. So that requires a holistic view, and together all these points, if you think about it, that requires significant rethinking on IoT security, and they are definitely not just solving the embedded security problems. There are a lot of new challenges. So before I go into the solutions, let's talk about some example attack scenarios. And some of these attacks are done in our research lab. This is led by my colleague, Professor Jean at University of Florida. He's a resident hacker in the university. And Professor Jean and his students, and in collaboration with us, he has been able to hack about 100 or a little bit more than 100 IoT devices. Okay, so I'll talk about some of them, but before that, let's take an example. Let's look at this example, which has been extremely prominent example of how IoT can be a huge security problem. In 2016, October 21, there was a widespread cyber attack which led significant part of internet services in America, United States of America, as well as in Europe, down for a long amount of time, which led to some of the key services like Amazon, CNN being unavailable for a long time. So what was the reason for that? The reason was very interesting. The reason was probably the first time in the history of mankind, a bunch of IoT devices were used by some of the naive attackers. I would say not naive, but some of the really young attackers in their 20s. These attackers were able to use close to 600,000 IoT devices. And these are baby camera, in their residential gateways, their printers. These IoT devices were hacked by by a some young hackers who were able to insert or install something called a botnet, which means that they were able to remotely control these IoT devices and insert a botnet or malware called Mirai botnet, and that botnet gave them access to those IoT devices. By having access to the IoT devices, they were able to create millions of fake DNS lookup requests to this server of this company called Dyn. And Dyn is a company which gives you the DNS lookup capability. That means if you type, let's say, a specific address like www.amazon.com, it translates that address into an IP address. It's called DNS lookup, and Dyn was responsible for that. By creating millions of fake DNS lookup requests, these attackers were able to bring down the servers in this company. So that led to widespread shutdown of internet services in large swaths of United States and Europe for a long time. So it's a coordinated botnet of IoT devices where these compromised or hacked IoT devices were used for the first time in the history of mankind to create a significant, powerful cyber attack. Now, how did they do that? If you ask me that question, the answer is actually very simple. What they did, they were able to install the Mirai botnet in these devices because these devices had about 60 of different types of these devices. They had the login and password, administrative login and password unchanged by unsuspecting users. So user did not change the default login and password, and that list of login and passwords for about 60 different devices were known to these attackers. And using those login and password for those devices, the attacker of about millions of 1 million devices, actually less than 1 million devices, were able to install this Mirai botnet and control them remotely and then do these fake DNS lookups. So it basically shows you that IoTs are becoming a powerful weapon for creating cyber attacks. And that's really a really powerful example to establish that fact. But in our research lab, we have done a lot of experiments with commercial IoT devices. This is a security flaw we discovered. Again, Professor Ierjin is the lead here. He basically was the first one to take a Nest thermostat and then break into it by looking at the different boot mode of the microcontroller used in that device, and he was able to run YouTube video on that. So let me see if I can run it. So basically, he and his students took the first generation of Nest thermostat and then let it boot a different code, not the original code that came with Nest, but it was able to boot different code. And by doing that, they were able to do anything they wanted with that Nest thermostat, including running a YouTube video. So you see that these devices, even if they're coming from really reputed companies, they did not have enough security or enough countermeasures built into them to prevent different types of attacks. So that's the thermostat, but we have really tried with all types of IoT devices. And again, I will basically quickly go to the next one. In this particular case, we are looking at surveillance cameras, and we tried different surveillance cameras. So by using this surveillance camera in different locations of the earth, we are able to figure out their security vulnerabilities, and we are able to even remotely see what these cameras are seeing. So that's definitely a significant vulnerability. If you can peek into anybody's surveillance camera, that's a huge security problem. I think you can understand that. And this is some of the examples which we did in our lab to show that these cameras, which you can buy from Amazon or any e-commerce website, or even brick mortar website, you can effectively compromise them. And that means that these devices do not really come with good security measures, and they're extremely vulnerable for potential compromise. Not just cameras, not just smart thermostats, we also looked at the smart meters. The smart meters as you know, they are replacing the traditional meters, which will basically monitor the electricity consumption at your place. And these smart meters can be compromised. And we took some of the smart meters, the commercial ones, we bought them from the market, and we were able to completely compromise them. It basically, in this particular video, you see that you'll be able to see that we took the smart meter. And the smart meter, our students were able to basically break the smart meter by using a security vulnerability in their communication protocol. When he's talking to another device, it basically assumes that device is trustworthy, and thus that device can fake itself to come up with a specific attack. It is called civil attack, and by doing that attack, the smart meter reading can be made to zero. So it basically means that even if you are consuming a lot of energy, effectively as a user, you can reset the reading so that the provider do not get the right amount of or the right bill for a specific usage scenario. So that basically shows you a spectrum of vulnerabilities the IoT devices come up with. So not only they can be used as a weapon for cyber attack, as happened for the Dyn cyber attack, but these devices, these are the edge or endpoint devices themselves, have significant vulnerability. So the question is that if they have so much of vulnerability, how do you address them? One of the solutions which we are looking at in our research lab is to come up with a hardware-centric solution where the hardware can provide the root of trust or trust anchor for the entire stack, and that will effectively allow you to make the system secure and trustworthy. So this is something I wanted to write here. The reason is that cybersecurity experts typically consider the hardware to be trustworthy. So when they build the software stack or when they build the communication layer, they assume that the hardware is secure and trustworthy, but that assumption is no longer valid. Why it's not valid? I will talk about some of the attacks that can happen on the hardware, and I'll talk about how hardware can protect itself as well as it can provide you a good platform to build secure, trustworthy software stack and communication stack. Before we talk about that, let's zoom out and let's see what is hardware. When you say hardware, we are talking about electronic hardware here. In electronic hardware, you can think about it as three different layers of abstractions. At the topmost layer, you have the device itself. Let's say, in this case, it's a thermostat, right? So that device itself is a hardware. And if you tear open the device, you will see something called printed circuit board, which all of you are familiar with. And this printed circuit board provides a mechanical platform and a way to do electrical connections among all these components that you need to integrate to make your electronic circuit, right? So one of the most important components in the board for any IoT device would be the CPU, and it can be typically implemented by a microcontroller. Dennis talked about a very nice tutorial on selecting microcontroller. That's definitely a wonderful one. Because that's a significant problem for IoT designers. Now, that's one of the most important components, integrate circuit components in any IoT device. The same thing happens for a smartphone. If you take that smartphone, you can divide the hardware into three layers: the device itself, then you have the printed circuit board, and then you have the system on chip or microcontroller, or sometimes it's also implemented by an FPGA. So these are three layers of hardware. Now, if you think about this hardware is supposed to be the root of trust, right? That's what we assume today when we run an apps, or when we run even a system software. We consider the hardware is the root of trust, and it should be secure and trustworthy. But that's not quite true, because there are so many different security issues and trust issues. The trust issues come into play because this hardware goes into goes through a very complex life cycle, and in that complex life cycle, there are multiple untrusted facilities, multiple untrusted people or users which you can encounter during this entire life cycle. So this is a typical life cycle for electronic hardware, where we start with the design spec. It goes to an integrated circuit design house, let's say Intel, Qualcomm, or so, or Broadcom, or Samsung, or Apple. And then once they finalize the design, they create something called GDS2 file, which is a way to describe the layout for the circuit. And that GDS2 file is transferred to a fab, which is a multi-billion-dollar facility. It's also called foundry, where we fabricate the chips. The chips are fabricated in the form of the circular, typically 12-inch wafers. The wafers have multiple chips implemented on that, and they are implemented through hundreds to thousands of complex set of steps. After the wafer is ready, we do some wafer testing to make sure everything is fine. And then on the wafer is tested to be fine, then we basically do the assembly and packaging, which means that we cut the dies by a diamond saw and then wrap them around with um, ceramic or different kind of packaging materials. We have the pins coming out of the package, and then finally the packaged integrated circuits or chips are tested using a complex functional and parametric testing procedure. After that, we integrate we create the system, we create the printed circuit board, put the firmware, and then we create actual system. So that's the process. During the process, there are multiple stages can be untrusted depending on the business model for the company. For example, typically foundry is untrusted because most semiconductor companies will outsource their design to an untrusted foundry. The PCB system integration facility can be untrusted, and then the other ones can be either trustworthy or untrustworthy. The YOLO means it can be either depending on the business model. So only thing you can trust absolutely would be the design spec. So with that in mind, there are multiple security issues that can happen on the hardware during the life cycle. And this slide is a very important one, which shows you what can happen on the hardware itself and what we need to worry about, right? And this is not just specific to IoT, that's true for any electronic system, but I'm talking about this because for IoT, it's also extremely important. We need to know what are the issues at the hardware level. For the hardware life cycle, typically today, the hardware is designed by having small intellectual property blocks from different IP vendors. One of them can create the memory, another can create processor, third one can create the communication engine. Together, that goes to the system on chip design house. They will assemble them, integrate them into a complex chip called system on chip. That design will go to the foundry, and the foundry will create the chip. Eventually, after system integration, it will be deployed. During this time, there are many different attacks that can happen on the chip. For example, one can insert a malicious circuit called hardware Trojan. One can do piracy of the IPs. That's very important from the IP vendor's perspective because they have to protect their IPs. One can overproduce, one can leak secret information. It's also possible to do reverse engineering and cloning of the design. How do you protect against these problems? This is an emerging area of research. I would say not very old. It's kind of about 7 to 8 year old. I've been involved in this field for almost the entire duration of this field. And we have come up with, in my research lab, we have come up with a lot of point solutions to deal with these threats. We can come up with design solutions, we can come up with testing solutions or verification solutions to deal with the problems. We'll talk about some of them, but let's just argue why a problem on hardware is so important. Why you need to care about hardware compromise, right? This is a slide which I borrowed from Semiconductor Research Corporation, and they are the one who showed this slide. It basically tells you that if you think about a system, let's take IoT as a system. So IoT has different layers of abstraction. You go from hardware to, to operating system, then application layer, and the user layer. And each layer you can have different types of compromise, right? Different types of attacks. security attacks that can happen at each layer. For example, in the user layer, there can be phishing attack, which are based on social engineering. Someone can send you an email saying that, hey, there is $1 million in a bank account of a Nigerian prince, and you need to give me your account number so that I can transfer money. So these are the phishing attacks which play with the psychological weakness of all of us, the human being. But that typically affect only few people, right? 1 to 100. If you think about malware attack, it typically affects 10K to 100K. Viruses and Trojans, these are software Trojans, they affect operating system. But even then, it only affects, let's say, millions of them, hundreds of millions. But if it's a hardware compromise, let's say if something that happens in Intel processor like Spectre and Meltdown kind of attack that recently surfaced, or the vulnerabilities, let's say, they affect billions of the hardware. So if you think about a software issue in a microcontroller, you can easily guess how many of those devices would be compromised immediately. So that's why hardware compromise and hardware security is extremely important. And some of the significant attacks that can happen on hardware, let me just quickly take a look at those, and then we'll talk about solutions. So one of the attacks that can happen at the hardware level is called counterfeiting attacks. So instead of having a really authentic integrated circuit or PCB, you can have a fake one, right? And it's a really booming business. It's there for a long time. But if you look at this plot, you can see about 25% annual growth rate for the counterfeit electronic component business. It's growing significantly, and many of the components which you use in IoT devices and other low-end devices can be fake chips, can be fake electronic components, and so you need to come up with solutions to make sure that the electronics which you use are not fake, because if it is fake, it comes with reliability problem, it comes with functionality problem, and of course, if you think about a legitimate IP owner, you are really depriving that IP owner from the royalty, and that's not a good thing, of course, right? So there are some real life examples that came out in our IEEE Spectrum article in 2017. For example, on the left hand side, you see a genuine and fake Canon speedlight flash. It's very difficult to understand from the look of it which one is genuine, which one is fake. The middle one is a Cisco router. That's a very interesting story because Cisco came up with this router, and then the attacker or adversary came up with an exact same copy of the router. And as you can see, looking at these two PCBs, it's very hard to understand which one is original, which one is fake. And interestingly, the one which is fake, they fixed some of the problems of the original one. So they were selling very well. And of course, Cisco was not happy about that. These fake components can be also integrated into cars. So for example, the Honda S300 PCB was that's part of the engine control unit in Honda cars. That was fake, and Honda came up with a disclaimer that there are a lot of fake engine control units there. So another problem that is getting significant attention today is that the hardware, let's say microchip or PCBs, they might have malicious component in it. An attacker can put a malicious component, also called hardware Trojan, into it. It can come in different forms, different factors, different sizes. It can do ideally two different things. It can create malfunction or lead to denial of service kind of attacks, or it can leak secret information from inside the chip. If it does any of them, of course, it's a significant problem for the legitimate users. It's called Trojan. I'll not go into details about that. But detecting a Trojan, it's a huge problem. It's creating a new field of verification where researchers are trying to come up with ways to detect a malicious change. Now, a malicious change is much more difficult to detect than a normal bug, because typically normal bugs are unintentional. Normal bugs are bounded by the spec. However, if you think about a malicious change, you're intentionally put inside the design so that they avoid the conventional verification methods, and they create extra functionality that's much more difficult to excite and detect than are normal unintentional bugs. So in our research lab, we have come up with a number of solutions to detect these malicious components which an attacker can intentionally put into a microchip in an untrusted foundry or into a printed circuit board when the foundry which is making the printed circuit board is untrusted. So we came up with something called statistical testing approach to detect it, and it's a really new paradigm for detecting unwanted, undesired functionality in a microchip. It can be extended to a printed circuit board. But this is called MIRO, multiple excitation of rare occurrences, where we develop a statistical test generation approach to excite rare conditions with high probability and then detect a malicious component inside a chip with extremely high confidence. So there's a paper on that. That's a functional testing approach. We came up also with a side channel approach where we looked at the effect of a malicious circuit or Trojan into physical parameters like a side channel parameter, right? So these physical parameters like supply current or delay, these parameters um, were carrying a fingerprint for a Trojan. And these fingerprints can be captured by measuring them and then removing the process induced variations and then detecting the fingerprint of Trojan in a side channel parameter. This is again an ongoing research. It requires golden chips to calibrate. We also come up with something which doesn't require a golden chip, where a chip can compare with itself. The idea here is that if you look at a chip, there's a lot of self-similarity inside a chip. So one can actually compare the side channel signature of one component of the chip with the side channel signature for another component. For example, in a microcontroller or processor, you can have multiple adders. So you can look at the current signature of one adder with another adder, and then that can lead to detection of a Trojan, because the assumption here is that the attacker will not put a Trojan in all these components at the same time. The Trojan can be also caught by looking at the temporal behavior of a circuit. If there is a Trojan, it's expected to behave in a specific way. So by comparing the current signature across multiple time windows, you will be able to detect existence of a Trojans with high probability. Another interesting attack and corresponding solutions which we are exploring in our research lab is called physical attack. And in this particular physical attack, we looked at printed circuit boards like the one in a gaming console or set-top boxes. And we're looking at physical modifications in those PCBs. It's very easy to do those modifications. There are YouTube videos where you can figure out how to modify the printed circuit board in your gaming consoles, particularly the older ones, to bypass the digital rights management protection or any other security protection. If you do that, then of course you can alter the functionality. For example, in a gaming console, Sony gaming console, you can play Xbox games and vice versa. And this is an attack which is becoming more prominent in the IoT regime, because many of the IoT devices like a drone are vulnerable to physical attacks. Somebody can capture the drone and alter the circuit and thereby retrieve sensitive information or manipulate the drone in a way which is not intended. So we came up with a solution. It's based on creating a fingerprint for the PCB, where the PCB creates a signature encompassing the entire set of components using the JTAG infrastructure, and then gives you a fingerprint which can be changed if you are modifying the PCB. So it's a very sensitive approach, very reliable approach. We also came up with a communication protocol where that signature can be securely communicated to a base station, which can verify the hardware health of the device during operation. So that's about physical attack. We also came up with an architecture level solution that was published in IEEE Spectrum 2017, where we came up with a hardware patching mechanism. I mentioned that IoT devices require patching because security requirements evolve over time. How do you patch a hardware? We can patch software, but how do you patch a hardware? So to do that, I came up with an architecture level solution. Before I go into that, let's just look into a traditional system on chip today, which goes into your cell phone or which goes into your iPad or other smart devices or wearable devices. This system on chips today contain a lot of security assets. For example, It can contain different cryptographic keys or configuration keys. It can contain sensitive firmware, sensitive personal data, and many other things which need to be protected. How do you protect them today? You protect them by using security policies. For example, if you go to Qualcomm or NXP or Apple or Samsung, they try to protect these assets on chip by having a number of access control policies which govern the confidentiality, integrity, availability of these assets. I'm not going to details about that, but what we did, we came up with a way to to implement these policies which govern the assets on the chip, and we called them infrastructure IP for security. In the later version, we also call them security engine. That is a reconfigurable fabric which can be updated in the field through over-the-air upgrade. And this particular security engine or infrastructure IP is basically an IP connected to all the other IP blocks in the system on chip that can be upgraded as needed. And that's the one which is implementing all these security policies in a centralized, in a configurable and flexible fashion. So we have published number of articles on this idea. It has been funded by Semiconductor Research Corporation. Multiple companies are interested in using that. So we'll just talk about another solution called hardware virtualization. If you think about virtualization, it's a common practice today to have a software virtualization, but in hardware, it's a new concept. But if you can do virtualization on the hardware, then it really helps us to map an application in that virtualized hardware in more effective manner and more secure manner. So this is an example where we are virtualizing a PG or field programmable gate array. What we are doing basically is that we take the FPGA and we create a layer on the FPGA on the physical primitives, and we map an application on that layer. That layer is called overlay, and we came up with our own compiler to map an application into that overlay. The advantage here is that now a designer does not really need to know the Verilog or VHDL kind of language and do detailed analysis on the physical primitives. So we're creating a layer on a layer of an abstraction, layer of abstraction on the hardware so that one can effectively and easily map an application to that and also implement security measures. So I'm not going to details about that, but having a virtual layer like in software gives you significant security advantage. It can also allow to make each of these devices unique by adding a secret key, configuration key at each of these units. So with that, let me talk about the final slides. If you really want to make IoT secure, then you need to have integrative measures. When I say integrative, just having one solution at one layer is not enough. You have to incorporate security solutions at each of the IoT layers, at each of the IoT devices. And not only that, even inside a device, you need to come up with integrative countermeasures. For example, you need to combine solutions which are used at the design level with the solutions which are used at the verification or validation level. And finally, you need to combine that with security monitoring solutions. If you do all of them, that gives you the highest confidence, and that also allows you to trade off security with the overall economics of a system. So that's my parting message. If you want to have a secure IoT, then you need to make it secure through design, validation, and runtime adaptation, a combination of that. With that, I'll just thanks my colleagues and collaborators as well as sponsors who have been responsible in doing all these collaborative works and which has funded the project and the students. With that, thank you very much for your attention. I'll be happy to take any question.
Thank you very much, Swarup. And with that, guys, please, whoever would like to send questions for Swarup, go ahead. Either you can send them in the chat, and so Swarup should be able to answer them here. Or I'll probably, Swarup, I think I'm going to unmute everybody. So anybody has questions they can ask and we can have a quick chat with each other.
Sure.
It will be a good opportunity. to talk to everybody as well.
Yeah, sure, please do.
Hey, Swarup, it's Dennis. Can you hear me?
Yes, hey Dennis.
Yeah, so that's a great, what a wonderful talk. And I guess you got to the meat and potatoes of it. I guess the second half was really, I guess, the key, what I was really interested in. I find it astounding that it's possible in a foundry process for a Trojan hardware to be inserted in the design files. Is that really happened?
So yeah. So if you ask me about real evidence, these evidences are rare. Rare means that, of course, any company who has things like that, they will not disclose. One can even argue that why would a foundry do that, right? So that's a very common question one can ask. Why would a foundry do that? Because that can affect their business. But what we are talking about here is that potentially a nation state trying to do some harm to another nation state, right? If you come to that, then of course that's possible. Now, when it comes to hardware, because of the significant impact of a hardware compromise, I talked about the numbers, right? A compromised hardware can lead to billions of compromised systems. Because of that impact, um, for hardware vulnerability, it's important to be proactive. In software, we are often reactive. You find a problem and then you install a patch. In hardware, unfortunately, we have to be proactive. And so to answer your question, there are some evidences of microchips with Trojans in it, right? People did not disclose how that happened, but they figure out that there are microchips with Trojans in it. I gave you one example in one of my slides. But the examples are not not too many. The reason is that these are the scenarios which nobody want to talk about. The manufacturers, the foundry, nobody want to talk about that, but they appreciate the vulnerability. And that as a researcher, that's what we care about. We care about the vulnerability as opposed to real attacks. Does it answer your question?
Yes. Yes, it does. Thanks, Swarup. I'll let someone else ask another question.
Sure.
So please go ahead. If someone has got a question, go ahead, unmute yourself. You should be able to now, and you can ask your questions. But I would have a quick comment as well, Swaroop. Interesting that you mentioned that Mirai, we were one of them, our organization or one of them, it got affected. And we were not using something, we were not using something small. We were using a large number of Sierra wireless modems with our vibration monitoring devices, and we were attacked by Mirai.
Oops.
Yep.
Yeah.
And a couple of our modems, like they have sent, I noticed that when I was going through the data consumption on those modems, I noticed that one of the modem was, in 2 days, it consumed almost 1.4 terabytes of data.
Ooh. Yeah, it's very powerful malware.
Correct. This is the amount of data they've been sending out. If it would have been billed by the service provider, it could be thousands of dollars.
Yeah, I agree. Thanks, Jonas.
We are open for questions. Go ahead if you have.
I'm looking at the chat box just to see if anybody has put in anything on the
You
chat.
can also type your question in the chat box as well, and Swarup should be able to see it.
Did you you unmuted everybody, or you gave them the
Yes,
ability
they
to
should
unmute?
be able to, and I did on my end, so they should be able to unmute themselves.
Okay.
If anyone having trouble unmuting themselves, let me know in the chat box.
Okay, so I think if they have questions, they have my email address. They can easily find me by Googling my name. Feel free to email me any question you might have. I'll be happy to talk about any of these topics and do a deeper dive and answer your questions.
Well, that's good then.
I have one more quick question, Swarup, before you
Sure,
go.
sure.
Yeah. On one of the slides, you talked about a PCB signature. I guess yeah. What is a PCB signature? What goes into making a PCB signature?
Yeah, so PCB signature.
In
That's a
15
good.
seconds or less.
Sure. No worry. PCB signature is a signature for the entire PCB, which means that if you replace one of the chips or if you even change the interconnect of the PCB, that signature would change. The way we create that signature is that we look at the JTAG infrastructure, which is this architecture that is typical for modern PCBs to do design for testing. So in that, the chips are connected in daisy chain. So what we are doing, we are looking at delay-based signature, like a PUF, physical unclonable function, coming from the PCB, and that represents collectively the identity of each of these components. Not all, but some of the most critical ones. So that if the attacker is either replacing a component or doing some alterations on those components, that will be captured in the signature. We call it PCB fingerprint. And that can be a good way to monitor if somebody is doing anything bad to the PCB.
Thank you.
That's a very good question. Thanks, Dennis.
So Swarup, how would you know? Like the general perception is, let's say if you have got something smart, a smart something, a best way of dealing with security vulnerabilities is to upgrade your firmware. But the devices like light bulbs, Nest, a thermostat controller, or something like that. I mean, I doubt it if an end user or even somebody who knows a little bit about computers or IT, they can handle with that.
No, today you are right. Absolutely, today there is no way to even install a patch in a smart light bulb because there is no operating system. There is no mechanism to even install a patch. Right? Installing a patch is not easy. That has to be supported by the operating system. And it needs to make sure nothing is broken during the installation of the patch. So it's a really big problem. And unfortunately, these devices do not come with a mechanism to install a patch. So if they have a vulnerability, we have to live with that vulnerability or buy a different one probably.
Okay, yeah. So, so that is it. I don't see any questions here, Swarup, and I think, as you mentioned, that they can search you on the Google. They should be able to send you questions or any comments or something else. Guys, if you have any comments, questions, or if you would like to participate, please do send myself or Dennis Sisek an email, and we should be able to involve you guys in the chapter. And if you have got some presentations, something that you would like to share with the community, please feel free to contact us, and we should be able to. You should have all my email address because I've been communicating with you from the beginning. So that's one of the contact, and that's it. Swarup, thank you so much. Dennis, if you have to say something, I would refer it to you to do the closing remarks. And thank you from me, guys.
No, thanks. Thanks, Swarup, for joining us this evening, and thanks, Eunice, for running this call.
You're welcome, guys.
Yeah.
See you next time.
Yep. Take care, Swarup. Thank you.
Thank you.
Yeah.
You too.
Bye, guys.